Section 2.3. The Vsepr model, valence shell electron pair repulsion. So there are rules. First, some definitions. Every single double or triple bond is one electron group. A triple bond consists of 6 valence electrons, but that's counted as one electron group. Each lone pair is an electron group. What if you have unpaired electrons? Well, it's one electron group. Lone pair electrons are more diffuse than single bond electrons, and thus the lone pair electrons can better repel other electron groups. A double or triple bond consists of 4 or 6 electrons. Although it's counted as one electron group, it can better repel other electron groups. And now the essence of the Vsepr model is very simple. Electron groups repel each other. You better separate the electron groups. So what if you have 2 electron groups, and then it's going to be a linear electron geometry. 3 electron groups, trigonal planar. 4 electron groups, tetrahedral. Over here, 4 electron groups. 1, 2, 3, 4. These 4 bonds are 4 electron groups, tetrahedral. 5 electron groups, like in this PCl5, trigonal by pyramidal. So 1, 2, 3, 4, 5. 5 electron groups. 1 pointing up, 1 pointing down, 3 in the middle. So these 2 are axial positions. These 3 are equatorial positions. And finally, octahedral. So this is simple. It's just up, down, left, right, front, and back. 6 electron groups. So it's very important for you to realize that I was talking about electron groups. I was not talking about molecular structures. It just happens that in these 2 cases, the electron geometry is the same as the molecular geometry. However, just if, I replace this chlorine with 1 lone pair electrons, I would still call this trigonal bipyramidal. Okay? When I refer to the electron geometry. Okay, if I put 2 electrons here. And then if I talk about the molecular geometry, well, I would say it's a trigonal pyramidal structure. If you're talking about this PCl4 with a lone pair here. What if I put the lone pair here? Well, I can replace this chlorine with a lone pair. Its electron geometry, again, is still trigonal bipyramidal. No change. Okay, even after we replace this chlorine with a lone pair. However, its molecular structure is called a seesaw. So look at this seesaw. Just imagine one kid sitting on here, one kid sitting on here, and this is the ground. Now let's look at a few examples. If you have a CO2 molecule, there are 2 double bonds surrounding this carbon. It's linear in this molecule. This carbon is surrounded also by 2 electron groups. This time one is single bond, one is triple bond. This water has a bent shape because its electron geometry is tetrahedral. Water is surrounded by 4 electron groups, 2 lone pairs, 2 bonds. All right. Ozone, actually, this is bent for a different reason. In ozone, the center oxygen is surrounded by 3 electron groups. So it's supposed to be, again, a trigonal planar structure for this ozone, if we're talking about the electron geometry. Okay, trigonal planar, electron geometry, and bent molecular geometry. Trigonal planar, BF3, we talked about this. Boron is surrounded by only 6 valence electrons. Over here, sulfur forms 3 double bonds with the 3 oxygen atoms. Ammonia is trigonal pyramidal because nitrogen is surrounded by 4 electron groups, including 3 bonds and then 1 lone pair. Right? CH4 is, of course, tetrahedral. And this is square planar because xenon, in this case, used its outmost shell electrons, 8 of them, to form bonds or lone pairs. So xenon actually forms 4 single bonds with 4 fluorine atoms, and then xenon has 2 additional lone pairs. So 2 lone pairs, one on top, on the bottom, and in the middle in the equatorial position. Xenon forms 4 bonds. So if we're talking about the electron geometry of this molecule, that's octahedral. That's octahedral. 1 lone pair on top of xenon, 1 lone pair on the bottom of xenon, and in the middle there are 4 xenon fluorine single bond. Alright, square pyramidal. I'm not sure about the entire structure, but I'm gonna guess the electron geometry is octahedral. So there's 1 lone pair electron on this SB. I forgot what's the name of this. Below SB, antimony. So there's 1 lone pair below antimony. And then 1 phenyl group on top of this atom, and then 4 surrounding this atom on the same plane. So the electron geometry is octahedral, but because we can't really see the lone pair electron on the bottom, its molecular structure is square pyramidal. Now finally we learn this PCl5, it's trigonal pyramidal, and in this case, without drawing the Lewis structure, I believe sulfur is in the middle, and then it's forming a double bond with this oxygen and a single bond with each of the fluorine atoms. I think the formal charge is on sulfur. Let's see what else. Octahedral. Well, that's simple. Sulfur is surrounded by 6 fluorine atoms, and then just 1 top, 1 bottom, 1 left, 1 right, 1 front, 1 back, 6 atoms. And the sulfur is surrounded by 6 single bonds. Its formal charge is 0, so that's good. You have a total of 12 valence electrons surrounding this sulfur. This structure, P minus, you can treat P minus just like sulfur. Sulfur has 6 valence electrons. Phosphorus has 5, so P minus has also 6 valence electrons. So this 2 share the same electron geometry and the same molecular geometry. Now over here, it says approximate shapes. It's because this oxygen is different from hydroxyl groups. But again, if you can just think about the 6 bonds, 1 top, 1 bottom, and 4 on the equatorial positions. More about Vsepr. So sometimes you have bonding electrons and lone pair electrons, and then you have different positions. Where should we, for example, put this lone pair electrons on sulfur in this electron geometry? This sulfur is surrounded by 1, 2, 3, 4, 5 electron groups, so it's trigonal by pyramidal. That's perfect. But we can put this lone pair on here in the axial position, or on here, equatorial position. So what do you think? Remember we mentioned this lone pair electrons are more diffuse. Bonding electrons are more localized, more confined. Lone pair electrons are more diffuse. Because the lone pair electrons are more diffuse, they tend to repel other electron groups more. So somehow we need to put it in a position away from other electron groups. If we put the lone pair here, the lone pair is going to have a 90 degrees with this electron group. 90 degrees, 90 degrees. So you'll get 3 90 degrees and then 180 degrees. Okay, so the 3 90 degrees are just too small. The repulsion between this lone pair and this bond is too big. So if I put the lone pair here, and then you have 90 degrees, 90 degrees, 120, 120. So let's focus on the smaller angles, 90 and 90. We have only 2 of them. If I put the electrons, lone pair electrons here, I have 3 90s. Now, if I put the lone pair here, only 2 90s. So this one is better. We want to minimize the number of small angles. That will help reduce the repulsion. So again, I'm going to show you another picture here. If I put it here, only 1, 2 90 degrees. If I put the lone pair electron here, 1, 2, 3 90 degrees. Just to emphasize, lone pair electrons are more diffuse. We're using a huge balloon here. So just imagine this balloon is repelling these 2 single bonds. Over here, this huge balloon is repelling this 3 single bonds really strongly.